Hello. This is Postgres FM. As usual, my name is Nik, Postgres AI, and my co-host is Michael, PG Mustard. Hi, Michael.
Hi, Nik.
And we have an unexpected guest today, Simon Eskildsen, CEO and co-founder of Turbopuffer. Hi, Simon.
Thank you for having me.
Yeah, thank you for coming. And it was very unexpected because we mentioned Turbopuffer last time and you messaged me on Twitter. And I think it's a great idea sometimes to look outside of traditional Postgres ecosystem. I think it's beneficial for everyone, should be. So yeah, thank you for coming, for sure. It's a great idea, I think.
Yeah, the origin story is kind of funny, and it was only a couple of days ago. There's a script where if Turbopuffer is mentioned anywhere, then I'll get an email or a summary. And you guys were discussing last time different ANN, like both in Postgres and outside, and Turbopuffer was mentioned. And so I just DM'd you and asked, hey, I come on, chat about Postgres, chat about MySQL, chat about like databases and when you choose one over the other, and when Postgres breaks for some of these workloads that we've seen, and when it's great. And now it's 2 or 3 days later, and we're on.
Including weekend, actually. So podcast was out on Friday, and we record this on Monday. That's velocity everyone should try to achieve. I like it.
Yeah, and you've had chicken hatch in the meantime.
That's why my camera is overexposed, because a whole night this camera I used it to broadcast. I didn't have time to tune it properly. But again, thank you for coming. This is about databases. This time probably not so much about Postgres, but definitely we should talk about vectors, right, and ANN, and maybe we should start from distance and talk about your background. And I've heard some MySQL is involved, right? Can you discuss it a little bit?
For sure. Yeah, my background is I spent almost a decade at Shopify, scaling mainly the database layer there, but pretty much anything that would break as the scale increased through the 2010s. Shopify, like most companies, started in the early 2000s, was on MySQL. So a lot of the work that I did was with MySQL, but also every other database that Shopify employed, like Redis, Memcache, Elasticsearch, and a ton of others, Kafka, so on. So I spent a long time there. When I joined, it was a couple hundred requests per second, and when I left, it was in the millions, and very, very intimate with the data layer there. I was on the last resort pager for many, many years, and that it has informed a lot about how I write software today. And a couple of years ago, I started a company called Turbopuffer because
sorry for interrupting. I remember Shopify, actually, we always recommend the article. Shopify had a couple of blog posts about UUID and how UUID version 4 is not good and version 7 is much better. And it doesn't matter MySQL or Postgres, the mechanics behind the scene is the same, how B-tree behaves. So I remember, and I think, Michael, we mentioned that article on podcast a few times as well.
We have mentioned it, Nik, for sure. And I think Shopify has come up before. I thought, is it a Vitess shop? I thought it might have been one of the early Vitess adopters.
Shopify is using a little bit of Vitess, but not very much. Vitess was not around when we did all the sharding back in the early 2010s, and so we did it all at the application layer. I wasn't part of the actual sharding decision, but I was part of a lot of the sharding work over the years. And it's funny because at the time I know that they looked at a bunch of proxies, and all of the businesses they later looked at had gone out of business. It's not a great business, unfortunately. But everything was done in Rubyland through just a module called sharding, and it did a lot of things and a lot of monkey patches into Rails. But let's talk about this UUID v4 thing, because I think if we wanted to do a pros and cons, MySQL versus Postgres, I spent quite a bit of time with both. And this one actually, to my knowledge, only really matters for MySQL. Well, it actually matters for Postgres as well, but in a different way. So on MySQL, right, the primary key dictates how the B-tree is laid out for the primary key, right? So for the entire row. So if you have UUID v4, it's completely randomly scattered along the B-tree. So whenever you're doing an insert, right, it will just kind of fall somewhere random in the B-tree, which makes the updates very expensive, because if you're adding 10 rows at a time, adds, doing 10 insertions that are in 10 different leaves, well, you're just doing a lot more disk I/O and your write information is high. In Postgres, of course, you're just appending to the heap with all of its drawbacks and benefits, and so it doesn't matter as much other than on the indexes, right? As my knowledge, But on the indexes, it will matter a lot, because on the indexes,
Yeah.
of course, it is sorted by that. And if you have some temporal locality, then it's not going to matter as much. So that's my understanding. So this matters a lot in MySQL. Now, that article, I think, was after I left. And Shopify doesn't use UUIDs as primary keys for anything. So I don't really know where this mattered. It must be something tangential, because MySQL really just does auto increment. And every shard does an auto increment with basically like with a 32K auto increment number. And then every shard has a plus offset into that to allow it to grow to 32K shards. Given how much of a pain in the ass it would be to change that, that's probably still the case. But I always really liked that scheme. So some tables over time at Shopify ended up having a primary key on the shop ID, comma the ID, because that would give locality for a shop. Because otherwise you have a lot of read amplification if you're trying to dump out a bunch of products for a shop, because the chance that there's going to be multiple products for a shop like in a leaf, unless you do that, is just a lot lower. So that ended up working really well. And this is a pain to do in Postgres, because if you want to rewrite the primary key or the heap by an ID, you have to rewrite the entire thing. That was one of my surprises, having worked a bit more with Postgres in later years.
Yeah. And I agree with you, and I agree that in Postgres it also matters, but only for B3 itself, primary key B3, if it's after increment, or in Postgres it's called big serial, for example, or auto-generated. Right now there's another method, but behind the scene it's also like sequence and it inserts. Oh no, in this case it's not sequence. There should be a function which generates UUID version 4, and if it's random, like version 4 is random, version 7 is closer to regular numbers, basically, right? Because it's monotonically growing, right? Lexigraphically ordered, right? So in this case, you insert only on the right side of B3, and dirty pages, if you think about how checkpointer is working. Also, in Postgres there is also overhead after each checkpointer is full page write, which involves indexes as well. So if you touch random pages all the time, a disk I/O overhead and replication and backups, actually everything receives additional overhead, while in version 7 we write on the right side all the time. It's much better. But heap is different. So I agree with this, and anyway, like I just wanted to say, we use MySQL article because it's written very well, and in Postgres we didn't have version 7 for quite some time. Last Thursday, version 18 release candidate was out, which will include full implementation of UUID version 7, which was vibe coded on Postgres TV with like a couple of friends, just in Cursor, I think. It was not on Cursor, it was before that, but anyway, it was just it was created right online. We did it, and right now it took a couple of years to reach maturity, because Postgres always waits until RFCs are finalized and so on. Anyway, soon version 18 will be out, and UUID version 7 is inside. But I think everyone is already using, just generating it on client. Okay, great. So you had this great career, and then decided to create another. Can we call it database management system?
It's certainly a full-blown database. Underneath Turbopuffer is an LSM. An LSM works really well for object storage, and every successful database ends up implementing every query eventually, right, in the limit. And Turbopuffer will end up doing the same thing. But every good database also starts with some specialization, right? And our specialization has been on search workloads. I would say that it's by no means a replacement for Postgres. There always becomes a time where it starts to make sense to move parts of data into more specialized algorithms, more specialized data structures, and more specialized storage. In general, my hypothesis on when it's time to create a database is that you need two things in the air in order to create a generational database company. The first thing that you need is that you need a new storage architecture, because if you don't have a new storage architecture, some new way to store the data, ideally both data structure wise and also the actual medium that you're persisting on, there's no reason why in the limit the other databases won't do the workload better. They already have the existing momentum. They already have the workloads. In the Postgres case, of course, it's the classic relational architecture where you replicate every byte onto 3 disks. And this works phenomenally well, right? We've had this in production for probably more than 40 years, and it works great. It has high performance, it has a very predictable performance profile, and it works really, really well with the page cache or the buffer pool, whatever database you're using. The problem with this model is that if the data is not very valuable, this model is expensive. Every gigabyte of disks, a network-bound disks, is about 10 cents per gigabyte. And unless you are really risky DBA, you're going to run those disks at 50% utilization on all the replicas and on the primary. So you're paying for this disk kind of 3 times, which ends up with a whole all-in cost for 60 cents per gigabyte. And that's not even accounting for all the CPUs that you also need on the replicas, because you need the replicas to process the writes as fast as the primary. So you're kind of paying for the same thing 3 times. So the all-in sort of per terabyte cost, when you also take into consideration the D systems can be a little bit more memory hungry, is probably around 60 cents to $2 per gigabyte.
Per month, right?
Per month. Yeah, per month USD. On object storage, the base cost is 2 cents per gigabyte, right? And when we need that data in RAM or on disk, we only have to pay for 1. And we only have to pay for some percentage of the data to be in cache at all times, right? You mentioned Cursor earlier. Cursor is a Turbopuffer customer. And they don't need every single code base on SSDs or in memory at all times. They need some percentage in memory, the ones that are queried a lot right now, and some percentage on disk, the ones that are going to be queried again in a few minutes or maybe in a few hours. And so you end up paying a lot less because we only have to keep 1 copy of a subset of the data rather than 3 copies of all of the data. Now, that comes with a fundamental set of trade-offs, right? We want to be as public as that. You can't use Turbopuffer for everything. If you want to do a write to Turbopuffer, we commit that to S3, right? So by the time it's committed to Turbopuffer, the guarantee is actually stronger than most relational systems because we've committed it into S3, which takes a couple hundred milliseconds, but the durability guarantee is very strong. But if you're building a system like Shopify, well, you can't live with a commit time in hundreds of milliseconds. It's just not acceptable. So that's a trade-off that means that this is not a system that will ever replace a relational database store. The other downside is that because not all the data is on a disk or in memory at all times, it means that you can have tail latency. And that can be really catastrophic in very large systems that are doing millions of queries per second. If you can't rely on a very predictable query profile, you can have massive outages to hydrate the caches. I've seen these outages on disks, I've seen them, and just even the workload changing slightly can mess with the buffer pool in a way where you have a massive outage. So these two things may sound like small trade-offs, but they're massive trade-offs for very large production systems. But it might mean that if you have, let's say, 1 billion vectors and you're trying to store them into Postgres, the economics just don't make sense. You're paying thousands and thousands, if not tens of thousands of dollars in hardware costs for a workload that might cost tens or hundreds of dollars on Turbopuffer.
How much is it really, 1 billion vectors? If one vector is, what's like kilobytes?
768 dimensions.
Yeah. Well,
It's
some kilobytes.
It's 3 terabytes.
3 terabytes to store 1 billion vectors.
Yeah.
And also we don't have a good index for 1 billion scale. Yeah, I mean, in Postgres, PG vector, HNSW won't work with 1 billion. Yeah.
I mean, we could just run the math a couple of different ways, right? I'm not saying this is how it works in PG vector. I'm less familiar with it now. But even if you have 3 terabytes of data raw, you're probably going to need to store more than that. You might be able to do some tricks to make the vectors smaller, so you only have to store maybe, I don't know, a terabyte or something along those lines, right? But remember that a gigabyte of DRAM is $5 per month, and you need that 3 times on all your replicas. So you're paying $15 per gigabyte per month. So if you're doing that, if you have to store that 3 times, you put everything in memory, and you're somehow able to get it down to a terabyte, then you're talking about $15,000 per month, right, across the 3 replicas, just for the RAM alone.
Yeah, I agree with you. HNSW, it's like memory. Memory is the key, and creation of index takes a lot of time. And for billion, we already have issues with few million vectors scale. I know Timescale, which I now renamed to Tiger Data, they developed another index based on disk N from Microsoft, I think, which is more like for disk, right? But I agree with you, like for this scale, it's not convenient. But also, I think it's not only about vectors. This argument that we need to save on storage costs, and it's insane to pay for storage and memory as well when we have replicas and we scale. Like in Postgres, if it's physical replica, it's everything. Like, so you replicate everything, all indexes, everything. You cannot replicate even. There is no ability to replicate only one logical database. You need to get all logical, whole cluster. And it means that you multiply costs for storage and for memory. And it would be so great to have some tiered storage, maybe with partitioning, as much as automated as possible, and offload all data to S3 as basically you consider. S3 is great for this. And I remember I explored Turbopuffer through Cursor. It's great to see the documentation. I knew Cursor is using Postgres. It was a few months ago, but then I heard they considered moving to PlanetScale. That was before PlanetScale announced support of Postgres, so I was thinking, are they switching to MySQL? And then I saw vectors are stored in Turbopuffer. Great. Then I learned that several our clients who get consulting from us and use Postgres, they also store vectors in Turbopuffer. It was, I think, Photoroom, a couple of more companies. It was a surprise for me, and I started to think, oh, that's interesting. And then I checked your talks. I think you also mentioned there that if we, so there is this approach with SPFresh algorithm, right? Different. It's not HNSW, different types of index, but also some additional interesting ideas about economics you mentioned, right? Not only this sense. Can you elaborate a little bit?
I think it might be helpful to just talk at a very high level about the different algorithms to do vector indexing into. I'll try to simplify it as much as possible, and we can dig into it further if you want. Fundamentally, the simplest way to do vector search is that you just store all of the vectors in a flat array on disk, right? And then on every search, you just compare the query vector to all of those. The problem with that is that you very quickly run up against bandwidth limits, right? If you have a gigabyte of vectors and you're searching that at maybe 10 gigabytes per second, if you can exhaust the memory bandwidth, which is unlikely in a big production system, you're only doing, maybe 5 queries per second, and the query latency into hundreds of milliseconds. So if you have very, very few queries and you don't care about latency, this can be feasible on small scale. And lots of people are doing that in production. But if you want to search a million vectors in, less than a couple hundred milliseconds and maybe 10 milliseconds and as part of a bigger pipeline, you need some kind of index. The problem with indexing vectors is that there is no known way to do it in a perfect way, right? If I search for a query vector about a fruit or whatever, I know that if I'm searching for banana, I get the closest fruit. Maybe that's a plantain. I don't know, right? In the cluster. But you have to build an approximate index in order to make this faster.
Because of too many dimensions. For a small number of dimensions, there are approaches, and Postgres have them for years, but for hundreds of thousands of dimensions,
That's right. Yeah, there's KD trees and so on for the smaller dimensional space, which we can use for geo coordinates and things like that, and simpler geometry. So for very high dimensional spaces, these things fall apart. Cursive dimensionality, it's called. So they're very large is also important about the vectors. If you have a kilobyte of text, it can easily turn into tens and tens of kilobytes of vectors, which is why separating into cheaper storage makes a lot of sense. So there's two fundamental ways that you can index the data. There's the graph-based approaches, HNSW and DiskANN, were the two you mentioned before. And there's the clustering-based approach. The graph-based approach is phenomenal if you can store all of the data in memory and you have very high QPS and very low latency requirements. So if you have, let's say, 100 million vectors and you're searching that at 100,000 queries per second and you need very low latency, you're not going to beat HNSW. It's going to create a very, very good graph to navigate it with. The problem is that it's very expensive. And the other problem is that almost no workloads in the real world actually look like this. So HNSW got very popular because it's fairly simple to implement correctly and it's very simple to maintain. So when you create the graph, which is essentially just, points that are close in vector space or close in the graph, it's very simple to incrementally maintain. You put one thing in, you search the graph, and then you add it. There's very simple rules. You can implement something like HNSW in tens of lines of code if you did a very, very simple implementation of it. The problem with HNSW is that every time you do a write, you have to update a lot of data, right? In database land, we call this write-ification, where every byte or every page you update, you have to update a lot of others. And the reason for that is that you add something, you add a node in the graph, and then you have to update all these other things to do connections to that node in the graph. So this works great in memory because memory is very fast at updating and very fast at random writes. But the problem is also on the read path. So memory is very fast at doing random reads. You can do a random read at 100 nanoseconds, but a random read on S3 or on a disk is much slower, in the hundreds of microseconds to the hundreds of milliseconds on S3. And on a graph, right, you don't really, there's no speculation that helps, right? If you start at the middle of the graph and then greedily navigate the graph from the query vector to the closest matching vectors, well, every single time you do that, there's a round trip. And on S3, that's a round trip that takes hundreds of milliseconds. So you're sort of navigating from the root. It's like 200 milliseconds. You go out 200 milliseconds. You go out another 200 milliseconds. And in general, for HNSW on 1,000,000, this might be in the tens of round trips. So this gets very slow, right? This is in the seconds to do this on S3. And even on a disk, this very quickly adds up to tens of milliseconds. That's the fundamental problem with graphs. Now, disk ANN is essentially using a lot of the same ideas as other graph-based indexes, but instead of trying to have, the tens of round trips that HNSW has, that's very good for memory, disk ANN basically tries to shrink the graph so there are fewer jumps, right? So instead of 200 milliseconds 30 times, it tries to get it to maybe 6 or 7 times or 10 times by shrinking the graph as much as possible. That's essentially the insight in disk ANN. The problem with disk ANN is that after you have added more than 10 to 20% of the size of the data, you have to rebuild the entire graph, which is an incredibly expensive operation. That is absolutely terrifying to me, to someone that's been on call for large databases, to just have, you could max out 128 cores rebuilding this graph in prod, and it could take you down at 3 a.m. because you don't know when you hit that threshold. And if you don't do it, then the approximation start getting bad and you start getting bad search results. The nice thing about the graphs is just they have very low latency, but they're just very expensive to maintain. Now, the first way, then there's the other type of index, which are the clustered indexes. Clustered indexes are very simple to picture in your head, right? If you have a cluster of, let's say you took out every song in Spotify and you clustered them in a coordinate system, and you can visualize this in 2 dimensions. If you plotted all the songs, and the songs that are adjacent are of course also adjacent in vector space, and genres will emerge, right? There'll be a rap cluster, there'll be a rock cluster. You zoom in and you get, little subclusters, I don't know, death metal, black metal, I don't know what all the different rock genres are, right? Somewhere in these clusters. And you can generate great recommendations based on that, because you can look at, okay, what did Michael listen to, and what are some songs that are close by that he hasn't listened to, and same for Nik. So it's very simple. You create a clustering algorithm that basically just tries to divide the data set into clusters. And when you do a query, instead of looking at all the vectors, you look at, clearly the user is asking about a rock song, so we're only going to look in the rock cluster. And that way you divide down the number of vectors that you have to seek. Now, the problem with this is that if you have everything in memory, it's not necessarily as optimal, because you might have to look at more data than you do in a graph-based approach. And because RAM has such good random read latency, the penalty is not necessarily worth it if everything is in memory at all times. But this is great for disks, and it's great for S3, because I can go to S3 and in 200 milliseconds get gigabytes of data back, right? It doesn't matter if I'm getting a megabyte or a gigabyte, I can often get that in the same round trip time if I exhaust the network. So if you then go into S3, basically you have to download all the clusters. So let's say clusters.json to really simplify this. And then you just look at the closest n clusters to your query vector. And then you download, cluster1.json, cluster2.json, whichever ones are closest in 2 round trips. And now instead of on the graph-based ones where you're doing 200 milliseconds, 200 milliseconds, 200 milliseconds to navigate the graph, you just have to 200 milliseconds to get the clusters, and then 200 milliseconds to get all the clusters that were adjacent. The nice thing about these clustered indexes is that with algorithms like SPFresh and lots of modifications to them, we can incrementally maintain these clusters, because you can imagine that when you add a vector, you just have to add it to the cluster, and it's just one write. The write invocation is very low. Once in a while, that cluster will grow beyond a size. Let's say it's 1,000 elements long, and you have to split the cluster, and then you have to do some modifications. That's essentially what SPFresh is. And then there's a little bit higher write invocation. But it's stable in the way that you never reach this threshold where, okay, I've added 20% of the data set, I have to rebuild the entire thing, as you do in disk ANN. HNSW, you don't have to do that, which is why it's very, very, it's very nice, but it's just slow still. So SPFresh, we think, writes a really, really nice set of trade-offs where it's going to be a little bit slower, but slower in terms of, okay, instead of a search returning in a millisecond, it might take 5 milliseconds, and just no one cares in production for search. This matters for a point lookup into a relational database, but for search, it's a perfect set of trade-offs.
Question on the cluster splitting. Does that mean we don't ever need to rebuild the whole index? Because I think that was a limitation of the first cluster-based IVF flat, I think we started with in PG Vector, and that didn't have the splitting as far as I'm aware, and therefore we had to rebuild the whole index from time to time if the data changed significantly.
That's right.
And there was also merge, right? There was also not only split, there was also merge in SPFresh, as I remember.
Yes, there's merge as well.
Makes sense.
And because you might do deletes, which are also a pain. To my knowledge, PG Vector does not implement SPFresh. It is very difficult to implement correctly.
But also funny, I did a little bit research in May, I think, when I discovered Turbopuffer. I started reading about this. I saw original implementation was actually on forked Postgres, SPFresh. I saw some. You need to dig into it. Like in some Microsoft repositories, also I think some Chinese engineers were involved, something like there. Like I saw some repository which was like basically forked Postgres, and original SPFresh implementation was on top of that. Maybe I'm hugely mistaken, but I saw something like this. But it's hard, I agree. And I also recalled what I wanted to ask. I was lost in my previous question because it was too many things. I recalled in your talks you discussed that S3 is ready to store data. S3 is ready because over the last few years they added important features. Can you recall what you talk about at the talks?
Yeah, I mentioned that there were two things that you needed to build a new database. And there's a reason why a database like Turbopuffer hasn't already been built. It's a new storage architecture. It's only really possible now. The three things that have enabled a database like Turbopuffer to exist with this sort of pufferfish architecture, right, where it's, when the pufferfish is deflated, it's in S3, and when it's, somewhere in between, it's in SSD, and then it's in memory when it's all the way inflated. The reason that's possible is because of three things. The first one is our NVMe SSDs. NVMe SSDs have a new set of trade-offs. They act completely differently than other disks, right? SSDs are just sort of like the old SSDs were very fast. But NVMe SSDs have just phenomenal performance potential, where basically on an NVMe SSD, the cost per gigabyte is 100 times lower than memory, but the performance, if you use it correctly, is only about 5 times worse. And you have to, by using NVMe SSD correctly, is really that you have to put a lot of concurrency on the disk. But again, similar to S3, every single round trip takes into hundreds of microseconds, but you can drive a lot of bandwidth. Old storage engines have not been designed for that. You have to design from the day that you write the first line of code. Otherwise, it takes a very long time to retrofit. It happens to be that exact usage pattern is also what's very good for S3. NVMe SSDs were not available in the cloud until 2017, 2018. So this is, in database language, this is relatively new. Second thing that needs to happen is that S3 was not consistent until December of 2020. I think this is the most counterintuitive to most, because most of us just think that it always has been, but it hasn't. What that means is that if you put an object on S3 and then you read it immediately after, you were, as of December of 2020, guaranteed that it was going to be read after write consistency. The third thing that needs to happen, and this is very informed by the fact that I was on call for Shopify for so long. When you're on call for a long time, you gravitate towards very simple systems, and ideally systems that are constantly tested on their resiliency, so you don't get paged when something abnormal happens. Yeah. And for us, what was very important for us to be on call for a database for Justin and I was that it only had one dependency. And that dependency could only be one of the most reliable systems on earth, which is S3, Google Cloud Storage, right? And the other derivatives like Azure Blob Storage and so on. They're very, very, very reliable systems. But you could not build the metadata layer on top, right? So Snowflake and Databricks and others that have built on top of this in the last generation of new databases needed another metadata layer, some consensus layer like FoundationDB or their own Paxos or RAF protocol to essentially enforce the read after write consistency, but also to do various metadata operations atomically. But in late 2024, S3 finally announced that reInvent compare and swap. And what compare and swap allows you to do is to put a file, let's say metadata.json, you download the file, you do some modifications to it, and then you upload it again with a version number, and you only upload it if the version number is the same, right? Basically guaranteeing that you did an atomic and nothing has changed in the interim. Very important when you're building distributed systems, right? You can really implement anything on top of that, as long as you're willing to take the performance hit of going back and forth to S3. And of course, they have a whole metadata, Paxos, whatever thing to implement that. In GCS, it's Spanner, but I don't have to worry about that, right? That's for them to formally verify and whatever they need to do to uphold those constraints. Those were the three things that needed to happen, right? And that is requirement number one to build a new database. And so that's what was in the air for Turbopuffer to grab, right? The second thing that you need for a new database is that you need a new workload that's begging for that particular storage architecture, right? So for Snowflake and Databricks, we saw that we want big scale analytics, and it doesn't make sense also for the dollar per gigabyte that we have to pay in operational databases and adding indexes on everything. So there was a new OLAP workload, and there was or at least an acceleration of the OLAP workload with all the successful web applications, and then the new storage architecture on top of S3, but they had to do some more work because these APIs that I just mentioned weren't available. And the new workload now is connecting lots of data to AI, and this storage architecture is a very good fit for it.
Yeah, so that's great. Thank you for elaborating about these three changes at S3. But they also made another change recently, and they announced S3 vectors, right? What do you think about this comparing to your system?
Yeah, I think that S3 vectors is if you are writing the vectors once and you don't query them that much and you don't care that much about the query latency, it can be a useful product in the same way that you might be using S3 today. But S3 vectors doesn't do full text search, right? It doesn't do lots of these features that you need for a serious system. And even S3 vectors recommends that you load into OpenSearch. And so for archival of vectors, this can make sense. So they're still operational, but there's lots of limitations that would make it very difficult for it to go into production systems, right? If you do a query to S3 vectors, it takes hundreds and hundreds of milliseconds to get the result back. Whereas to Turbopuffer, you can get the result back in less than 10 milliseconds.
Thanks to cache, right?
Thanks to cache, yeah.
Yeah, that totally makes sense. I have skeptical questions, more of them, if you don't mind.
Let's go.
Yeah, one of them is your cache layer is on local NVMe's, right?
Yeah.
But why like we could store it there? Planescale recently came to Postgres ecosystem and they said, let's stop having fears about using local NVMe's and yes, like ephemeral storage and so on. And there is a reliable failover and so on. Let's do it super fast. Yes, I agree, it's super fast. And 4 terabytes for billion or 3 terabytes for billion vectors probably won't cost too much because this price is usually in AWS, for example, in the instances which have local NVMe's, it's basically included. And the limit is many dozens of terabytes of local NVMe storage these days on larger instances. So we are fine to store not only vectors but everything else. So my question is like back from S3 to MySQL, for example. MySQL supports storage engines for many years. Have you considered building storage engine for MySQL, for example, and using local NVMe? Right.
You can't outrun the economics, right? The economics are still the same. You have to replicate, whether it's local NVMe or not, which is not necessarily cheaper, maybe only marginally than a network volume. You still have to replicate it 3 times, right? You still have to put it on 3 machines. You still need all the cores and memory and so on that you would need on the primary to keep up, unless you start to have a heterogeneous replica stack, which for a variety of reasons would be a really bad idea. So you're still paying for all of that. Now, up to a certain point, that makes a lot of sense, right? If I have a customer who gets on a call with our sales team and they have a couple million vectors in PG vector, there is no reason to move off of it. That is perfect. You should not be taking on the complexity of ETLs and so on. But if you have like tens of terabytes of vector data, it is not economical for a lot of businesses. Now, for some businesses it are, right? But the art of a business is to earn a return on the underlying costs. And for some businesses, it's very, very challenging to earn a return on storing this on 3 replicas, this vector data. It's generally not valuable enough to the business. So Turbopuffer doesn't make sense as a storage engine into a MySQL or into a Postgres. It's just fundamentally not compatible with the way that we do things outside of replica chains, right? You could maybe come up with a storage engine where you page everything into S3 and all of that, but you're now trying to build a new database inside of an extremely old database, right? The storage layer is too, especially more so in Postgres, I think, than in MySQL, is very, very weaved into how the query planner works and all of that. So at that point, you're rebuilding the query planner to be very round trip sensitive. You're rebuilding a storage layer. It doesn't make sense anymore. It's a completely different database.
Okay, another skeptical question. I go to Turbopuffer website, and by the way, great design, very popular these days with monospace font and like these types of graphic. And you advertise for 1 billion scale, 1 billion vectors or 1 billion documents. But there, if I check 1 billion, the concept of namespaces pops up. And namespaces, it's if I choose 1 billion. If I choose 100 million, it's okay. I can have one namespace. But if it's 1 billion, there is a warning that probably you should split it to 10 namespaces. And this means 10 different indexes, right?
That's right.
Yeah. So it's not actual 1 billion scale. Or like something is off here in my mind. Like 1 billion is a single index, should be single index. If we talk about 1 billion but divided by 10 collections and indexes also, like it's already a different story. And so yeah, can you explain this to me? I saw this in the beginning, and I'm happy in this position. I can ask the founder himself about this.
Yeah, we try to be extremely transparent in our limits, right? And I think your mental model is correct. Before this, we just had a limit that said that we could do in a single namespace around 250 million vectors, right? But I mean, even that is a simplification, because how big are the vectors? If there are 128 dimensions, they are a lot less space, which is ultimately what matters here, which is why we also put the gigabytes. So when in the past we had just 250 million vectors on there as a limit, people came to us and said, or we knew that people weren't testing with us because they wanted to search a billion at once. And they didn't realize that you could just do ID modulus n, and then you could do a billion, and it would be very economical for them. So we sort of had to, put in the docs, like, yes, you can do a billion at once, but you have to shard it. Now, I would love to handle that sharding for you, right? I mean, that's what Elasticsearch does, and it's what a lot of databases do, because the only way to scale any database is sharding, right? You don't get around it. The question is where the complexity lives, right? Does the complexity live inside of the database to handle it for you? Like some of the most sophisticated sharding you will find lives inside of Cockroach and Spanner and these kinds of systems. And the simplest type of sharding is what we're exposing, where every single shard is just a directory on S3, and you can put as many of them as you want, and you can query as many of them as you want. Now, over time, of course, we need to create an orchestration layer on top of that so that a logical namespace to the user is actually multiple namespaces underneath. But we're challenging ourselves to make every individual namespace as large as it possibly can. When I ran an Elasticsearch cluster or was involved in scaling Elasticsearch clusters, every shard was around 50 gigabytes. That was roughly what was recommended for Elasticsearch.
Quite small, right?
It's quite small, right? Like on Postgres, it's a lot larger than that, right? It's basically the size of the machine. But the problem with a small shard size is that for something like a B tree, right? It's obviously like it's log n, right? To the number of searches you have to do, and if you have log n and n is very high, well, that's a great number of operations that you have to do. But for every shard, there's sort of like an m log n. And now m is very high if the shard size is small, and n is small. So you're doing a lot more operations. So we want the shards to be as large as possible, because of course you can get to a billion by just doing, 1,000 1 million shards, but like that's incredibly computationally ineffective. So we have shards now for some users that we're testing that do almost 1 billion documents at once, right? But it requires some careful tuning on our end. So we want to push that number as high as possible. The other thing with namespaces is that Turbopuffer is a multi-tenant system, and we have to bin pack these namespaces. So if a namespace is 5 terabytes large, it's much harder for us to bin pack on node sizes that make sense. So we have to walk some threshold there where we try to make the shards as small as possible from the logical data. We have to bin pack, and then we have to index without slowing the indexing down, because the larger an ANN index gets, the harder it is to maintain the index. So those are the constraints we walk. So over time, we update these limits continuously. You will see that shard size increase. But you're not going to find anyone who's doing 100 billion vectors in a single index on a single machine, aka M is 1 and N is 100 billion. But we want to get as high as possible because that is the most competitionally effective. That's how we get our users the best prices, and we see the most ambitious use cases.
And shards, are these actual shards or partitions? So it's like shards, meaning that different compute nodes behind the scenes are used. If it's 10 namespaces, is it 10 shards, 10 different compute nodes?
So a namespace for us, and this is also why we've chosen a different name for it, right? A namespace to us is a directory on S3. And which compute node that goes to is essentially just a consistent hash of the name of the prefix and the user ID, right? So compute node 1 could hash to maybe 100,000 different namespaces, and they share the compute, and then we scale the compute right with that, and that's why the bin packing problem comes in.
I see. Yeah.
Yes, and that's also part of why we can get really good economics.
Yeah, I wanted to shout out again the front page is beautiful. It explains like basics, architecture, and pricing right here, latencies right here, and case studies. This is like how it should be, right? For engineers, so you quickly see all the numbers and understand. That's great. Thank you for transparency. That's great.
I think it just comes from the fact that I was on that, your side of the table my whole career, right? I've been buying databases, evaluating databases, and sometimes I swear I end up on a database website and I don't know if they're marketing a sneaker or a database.
Yeah, go figure out storage or compute price in AWS or GCP. It's like always a task.
So we really wanted to just put the foot forward of like the diagram is right there. Okay, this is my mental model. This is what it does. This is what it costs. This is how fast it is. These are the limits. These are the customers and how they use it. You go to the documentation. We talk about guarantees. We talk about trade-offs. The kinds of things that I always look for immediately to slot it into my model. Because I don't want you to use our database at all costs. I want you to use it if it makes sense for you. I want it to be a competitive advantage to you. I want to save you like millions of dollars a year. And in order for that to make sense, you have to just put all the bullshit aside and make it very clear what you're good at and what you're not good at.
What about, for example, if I know there is vector search and full text search supported, right? But what about additional filtering when we have some dimensions when we want to filter on them? Is it possible?
Yes.
For example, some categories or like time ranges or something. It's all possible, right? In both types of search in Turbopuffer.
I'll go back to my line before of every successful database eventually supports every query, right? And I like maybe 5% of the way there. So we support filters, and filtering on vector search is actually very difficult, right? Because if you do something like, let's say I'm searching for banana and it's an e-commerce site and I have to filter for ships to Canada, well, that might cut off a fruit cluster, which is actually where I want it to be. And then I get to the banana on a t-shirt cluster, but it's really far away. So you have to do very sophisticated filtering to get good results. I don't know what PG Vector does, but I know that our query planner is recall aware. It does a lot of statistics and distribution of where the vectors are to ensure that we have high recall. And for a percentage of queries in production, we check against an exhaustive search what the recall is, the accuracy of the index. I don't know if PG Vector does this, but I know it's been a monumental effort for us to do it.
It's a big headache there. It's a big headache. Actually, it's a good point that additional filtering can change semantics of the search. If it's searching for bananas, size equals nano, it's very different.
One thing they've implemented relatively recently is iterative index scans. So I think they had a problem where, for example, you'd put a limit. You'd do a similarity search with a limit and a filter, and you'd ask for 100 results and you'd get back fewer, even though there were. So it's they had a problem, so they go back to the index and request more. So yeah, it's like a workaround, I'd say, more than a solution, but it's pretty effective for a lot of use cases.
I think the problem there is that I would be very skeptical of the recall in a case like that, right? Because, okay, so you got 100, but you probably should have looked at a lot more data to know what the true top K was. So, we that solution was not acceptable to us. Like we had to go much, much further to ensure high recall. And I think the problem with a lot of these solutions is that people are not evaluating the recall because it's actually very difficult to do. And it's very computationally expensive. You're not going to have your production Postgres run an exhaustive search on millions of vectors. Like, it's too dangerous to do that where you're doing your transactional workloads. But again, if you're hitting these kinds of problems, then it may be time to consider, maybe for a subset of your workloads, whether something more specialized makes sense, whether the trade-offs make sense to you. But I think with the pre-filtering and post-filtering, it's very challenging to create a query planner that can do that well. So we support all the queries, right? You can do range queries, you can do exact queries, you can operate with arrays, you can do all types of queries, set intersections that people use for permissions. We can do full text search queries, we can do group bys, we can do simple aggregates. So we can do more and more queries, and we're constantly expanding that with what our users demand from the system that we've built.
One more annoying question. I know it's not open source, there is no free version at all even. I'm pretty sure it was a decision not to go with open core or open source model at all. And can you explain why?
Yeah, I think there's never been any particular resistance to open source. I mean, I love open source. The reason we're not open source is because open source is it's if you want to do it well, it's a lot of effort. And it's also a lot of effort to build a company. It's a lot of effort to find product market fit. And we decided to pour all of our energy into that. And it's similar argument for the minimum. It's really the only thing that a startup has over, the big incumbents is focus. And so our focus has been on the customers that are willing to pay. And one day I would love to give a free tier. I would love for people's blogs to run on Turbopuffer. But for now, I'm afraid that we have to prioritize the customers that are willing to put some money behind it. It's not because we have provision hardware or anything like that. It's really just that we need to know that you're willing to put some money behind it so we can give you amazing support, right? A lot of the times there'll be engineers working on the database who are supporting your tickets, and we can't do that with a free tier.
Mm-hmm. Mm-hmm. Yeah, makes sense. And Michael and I have different points of view on this area.
I think that was a good answer. I'm on your side, Simon. I had a question on the full text search and semantic search. We had a discussion a while back about hybrid. I think it's generally called hybrid search. Are you seeing much of that where people are wanting to kind of mix the results and order between them?
Yeah, we do. And what we see is that the embedding models are pretty phenomenal at finding good results for subjects that they know about, right? And terms that they know about. You run a project called PG Mustard, right? And maybe the embedding model doesn't know. I think it's popular enough that it will know what it is, but let's say it didn't know. And then it puts it in the cluster close to ketchup. And the results are just horrible. And the full text search tends to be really good at this, like recall for things that the embedding model can't know about. If you're searching for an LG, these like TV SKUs, it's like, it's indecipherable. Actually, the embedding models are actually quite good at these because they happen enough on the web. But imagine that it wasn't. These kinds of searches it's good for. The other thing is search issue type. So if I'm searching for SI, the embedding model might find that, well, he's searching for something agreeable in Spanish, right? But really what I wanted was the document that started with Simon. So sometimes you just need to complement these two, and I think that's why we've doubled down on the full text search implementation in Turbopuffer to do this hybrid. But people can get a lot of mileage of embedding models alone.
Wonderful.
Yeah, thank you so much. Yeah, it was super interesting. Good luck with your system. And I think it's an interesting idea, I guess, for Postgres users who need, as you said, like to store more and have all characteristics Turbopuffer have. Maybe it's worth considering, right, to keep all OLTP workloads and data in regular Postgres while moving vectors to Turbopuffer, right?
I mean, it's just similar to, people have taken workloads out of Postgres. It's like updating a posting list is a very expensive operational and transactional store. And it's similar in an index, updating that with the same kinds of asset semantics that Postgres upholds is very expensive. And I've ripped full text search out of Postgres many times because it's very, very expensive to do. So we do that because we don't want to shard Postgres because it's like a lot of work. And so we start by moving some of these workloads out first. And search is one of the early ones to go.
So your point is that it probably postpones the moment when you need to shard. That's interesting.
Same reason for Memcache and Redis, right? You separate out these workloads as soon as possible to avoid sharding. Kick the can.
Interesting idea. Okay, again, thank you so much for coming. It was a super interesting discussion. I enjoyed it a lot.
Thank you so much.
Yeah, really nice to meet you. Thanks for joining us. Take care.